Yeah. So welcome after the tea break. I think I'm reachable, right? Yes. Or should I be aware of this? No need? Okay. So, well, I hope you enjoyed the talk, that the last 3 to 4 talks, right? What I will do is that I will not be more theoretical, of course, some mathematical portion will be there, right? If any confusion or clarification, you can interrupt me. Okay? Well, so what I will do is here that I will start from the basics, that why you use cloud, of course, you know it out, just introduction. Then I will discuss about that, what are the security and privacy issues are there, and how the trustworthy cloud making is a little bit difficult, and what the challenges are there, we'll discuss, right? Okay. Well, so if you look at this cloud service, of course, I think that no one will say that I'm not using the cloud service. Is there anybody? Nobody will say that I'm not using cloud, right? What the reason is? Why do you use cloud? Accessibility. Yeah, availability. But very important. I mean, right? The interesting thing is that you can access your data at anywhere, anytime. Okay. Anything more than? Yeah. That storage issue. Otherwise, I need to carry what you call the USB drive or something. Of course, now you will not find the floppy drive or CD. But you need to carry something like, right? Okay, that's there. Anything else there? Cost, right? Cost, right? Okay. If you see that if I want a particular server of some configurations, it may cost me around 10 to 15 lakhs. I'll pay certain amount, right, for a certain period, and then I'll use it. As and when required, I'll use it, and after that, I'll throw it away. That's the reason, of course, if you remember that many people say that the wiser the tenant, foolish the owner. Is it no? Is it not, right? So the meaning is that I purchased, of course, I think that I am also a foolish man, that I purchased the house just maybe 2 months back. I will not go there, of course, around 10 to 12 years, right? Somebody will enjoy that house, right? So I paid around 1.5 crores or 1.4 crores, but that fellow will give hardly 20,000 or less than that, which is much less than the EMI value also, right? That is 1 or 3 months, right? Isn't so, right? Therefore, particularly you are using it, right? You see that the storage what you are getting from the cloud, if you see that it is reasonably cheaper than that if you acquire it. Isn't so, right? Well, so it is about basically cloud. If you look at that, the concept is not a very new. However, the model is a bit newer. Of course, not nowadays when it is startup. Right? It is a business model, right? So that you use and pay, okay? Or you can say that, I mean, you say that prepaid basis you can pay and use for that time, right? That's one way or other, right? Right. It's not a new technology, of course. It is not like grid or client server. Okay. If you distinguish, many times I ask questions that the students that whether how you differentiate the grid and cloud. Can anyone answer it out? Okay, I will give you these things. You search it then, and then tomorrow you can tell me that. How will you define that? How the grid is different from the cloud? Okay, you look at the technology different. Okay, the business model is different for the grid and cloud, right? Okay, and it is not basically, it is also not like the client server too. Okay, so it is a new way to obtain the data center service. Cloud companies like online music and CDs, right? And we see that the data center, it is not in one place like your client server, right? We'll keep somewhere else, and you are doing it out, right? Right? Therefore, I say that it is not exactly as the client server approach. Well, it is user-based billing, access anytime, anywhere, customer control service provision, and modification and terminations, you can do it out, right? Well, the storage, if you see, the cloud is vital online technology that is used all over the world. 3.6 billion cloud users in the world. That is around half of the population in the earth. Right. Of course, it is counted even the small children too. Therefore, these things, right? Okay. 94% of the enterprise use cloud service. The reason already we discussed, right? Because it's cost. Right. Not only cost, the most important thing is management. You see that the things what you're facing in the IIT Patna, right? Sometimes when I was in the charge, I was thinking that can we just let us outsource things, and slowly we did it also. Right? The mail is not in our control. Mail is given to the Microsoft. Right? That's the basic things. The management, the administration is a really tough job for us. Right? That's it. Right? So 94% of the enterprise use cloud service. 67% of enterprise infrastructure is now cloud-based. Just we discussed that because of the cost, right? This is of course the market level, not right. If you see that the European organization top cloud initiative says that the right hand side, the graph says that the migrating to cloud optimized to cut the cost and cloud first strategy. This is just the what do you consider the opinion pool, right? Why is already I told you that no need for the external device to carry it out with you. Data is quickly and automatically updated in the cloud and available for your retrieval whenever you need it, right? Elastic size. Today I need some storage and tomorrow I need to, more than that I can do it. Tomorrow I need less, I can do it too, all right? So many cloud storage service provider, you know it out. I think no need to read it, right? So you see that what we do in the cloud, not only store, right? Many things beside the storing also we do it. I store the data and I process the data, and sometimes I ask the query to get the answer to. Isn't so? So these are the basic three operations we do it out. Let's see the challenge, what happens, right? So see, it is a service model in which data is maintained, managed, backed up remotely, and made available to users via internet. Okay, and many applications, of course, this is just I wrote it a very small, right? Healthcare, government organizations, and education organizations, right? Well, of course, this answer is yes, right? Already discussed, right? Well, so let's see what the trustworthiness of these, right? Right. Of course, though we understand that there is a lot of confusion on what the trust is. Because many of you answered correctly that what the trust is that I desire certain things, I have some expectations, and accordingly that I measure the trust, right? I say that the student is trustable means I have some desired features according to that, right? With corresponding to that student. It may not be same for another students. I could have another parameters. Right? Well, so a trustworthy cloud storage system must ensure the security that is protecting data from unauthorized access and cyber threats. Privacy, ensuring only authorized users can view or modify the data. I think today morning also he clarified it, the difference between the security and the privacy. I will provide entire things, right? Don't worry for things. I will I was already told that particular station I saw it was not available. I told him to buy sufficient pen drives with which I will give all the materials to you. And the last day, right? Okay. So privacy ensuring only authorized users. I think you can understand that how do you differentiate this security and privacy? Morning also I clarified it. How do you define it? What do you say that it is privacy, not the security? So I will tell that it is privacy.
Privacy is mostly used for the user's account.
Exactly. It is, which is user specific data, that I call it privacy, right? Otherwise, the features will say, right? I need to protect the data so that nobody can see it out. Right. Otherwise, if it ordinary data, I could say that okay, it is the data, right? Confidential. Make sense now? Okay. So the reliability guaranteeing data availability even during failures, right? So we say that robustness too. Integrated at preventing data tampering and ensuring the accuracy. Okay. Transparency, allowing users to verify storage and retrieval process. I think all the definitions already he told the basic definitions, right? Right. So transparency, if you really see that the exact meaning, if you say that okay, I can see it, but what you can see, that you need to understand. So we need the procedures, the process, right? Okay. Well, so the challenges of the data confidentiality, that is preventing unauthorized access to sensitive data stored in the cloud. Data integrity, ensuring stored data which is not altered by attackers or cloud providers. So this I am again highlighting it. Means the cloud provider himself or itself could be an attacker chip. I don't want to disclose my data to the cloud provider. Right? Right. I don't have trust on that. So when in sometimes when it comes that okay, we give it to the cloud system, when the provider, the vendor comes, we discuss with that. Their argument is that no, we don't see your data. But you see that if such is the case, why the data which is there? Every day we are looking at the data which here from the cloud system. We look at the Dropbox, even Google, Microsoft Cloud also. How it is come? And Facebook, you must have seen hard. So this is happening, but it is maybe intentionally or unintentionally. If God is existing, He knows, right? What is happening? Many times we could know also. Right? Well, availability and fault tolerance, guaranteeing data is accessible even in case of failure or attacks. Access control and authentication, managing permissions and preventing unauthorized modification. Transparency and auditability, that is allowing users to verify security policies and detect potential breaches. And the last, the legal and compliance, right? That is ensuring compliance with the GDPR, and in India we call it DPDP, right? Hope everybody knows, right? What is DPDP? Audit out?
Data privacy protection.
Not that exactly. Yeah, close to that, but exactly. Digital protection data privacy, right? DPDP rules, right? Well, so and the HIPAA guidelines for the medical data and the CCPA and ISO 27000 27001 security standards and so on, right? Well, let's have a small understanding that one cloud service like Amazon Web Service, which is very popular, how it works, and the claim that which is claimed to be the very secure and privacy preserving. Let's see that, okay? So let's say Amazon S3 object I created, or Amazon EBS volumes, or Amazon Redshift cluster, whatever I took it, I hired it, okay? Then I will encrypt it using the data key. And what I'll do is that, this is my encrypted things, and I'll encrypt the data key with another customer master key, whatever. Right. You see, a diagram is clear that for one object I made the different data keys, but master key is same. Okay. And this is my key, of course. I am the user. I have this key. This is my corresponding key. Now let's see the next part where I keep it. Okay. Let's see that. Okay. This is the things, and this is the key. Data key is encrypted here. Makes sense now, right? Well, so while it is in my machine, I am the client, right? This application or AWS service, the client, right? So I want to say I access the data, right? I stored it out. I stored it in encrypted way so that no one can see, right? So I want it out. So I need to encrypt the data. So I need to decrypt so that I can read it out, right? So I need to have the decrypted key, right? But so before that, let me say, okay, anyway. So I need to have the decrypted key, but with me, I don't have any it's a decrypted key, decrypted key. So what I will do is that I have a key, which is an encrypted key. I will send it to the management service, errors management service. He will map it with my master key, my ID and the corresponding master key. So using that master key, it will decrypt that encrypted data key, okay, and give the plain key to me, the data key to me. So I will take the data key and I decrypt it out, I get my data. Makes sense now? And when I encrypt and store it, I want to build this object, okay, and I need to encrypt it out. So while I encrypt it out, again I will do the same things. I request for a data key. What that fellow does is that he will generate a data key and encrypt the data key with using this master key and send this to both data key as well as encrypted data key to me. Hope it makes sense why I am sending, why he has sent the both. If he sent this only, then he cannot do anything. So I need the plain key, right? So he sent it. And why he sent this encrypted data key? You have to tell the answer after a minute, right? Let me tell you, explain these things. So take this data key, encrypt this data, and give it out. And what the fellow does is that he'll delete this data key, so that other people cannot attack me or cannot take my data key. So what I have now, the client only having the encrypted data key, right? So can you answer it out? What I asked the question? Why the encrypted data key is that? When the next instance of time, when I want to say that I need the corresponding data key, then I will give this. Because you see here, data key, these are the different. So I'll have the encrypted data key 1, encrypted data key 2, and so on, and I'll get it. So when I send this, he will decrypt it and give this key. I'll do this. Make sense now? So where the glitch is? So the glitch is that this master key is managed by this one. So why should I trust it? So that makes it challenging for me, right? Okay, that is. So here everything is good. That plain text keys are never stored in persistent memory and runtime systems. And it is, I am keeping only the encrypted data key, right? Separation of duties between systems that use the master key and data key. Master key is used for one duty, that is to encrypt the data key. And the data key is used to encrypt the data. And note that the data key is different for different objects. So that if one is compromised, others are not. Okay, that also taken care of. Everything is good here. Multi-party controls for all maintenance and systems that use your master key. Well, so it is called the envelope encryption. I will discuss about the envelope encryption and maybe the after a while, because he today told about the homomorphic. So I thought that many people got a bit different. So I thought that I told him that we will discuss first from my side the homomorphic, and we can tell. Okay, well, so this envelope encryption I will tell you in the next slide how it is happening. It limits the risk of compromising of data key. Others are safe. Easier to manage a small number of master keys than million of data keys. So the AWS system, key management system AWS is holding only the master key of a particular user. Make sense? Okay. Now, see the things that CSP claims to safely store the data. Of course, this is they say that, right? What is in your SLA, service level agreement? Will keep your data safely, right? Securely process the data, okay, and answer it correctly to your queries. Right? These are things what we need, right? You keep it And whenever I ask you, give it. And process my data also, because I don't have much more processing power, so that I can request to process and give it. Maybe some computers is required. And answer correctly if I want to do, and protect the privacy. Make sense, right? So the cloud provider knows the content, that's what I told. It is not hiding to the itself, right? Okay, well, and perform the computations, right? So now that once data is stored in the cloud, you don't have any control on it. I said that, okay, I will go and delete the data, but actually it is deleted or not, it's not that. Because you see the many breaches after deleting your data, after deleting some images, you could get it out. It is sold to data dark web. Must have heard, right? So what you delete, whether it is deleted from there or not, nobody knows, right? Okay, well. So secure data storage and encryption, data at rest encryption, and we do the end-to-end encryption too. So data at rest encryption in the sense, just what I told. Because the data will be stored at this cloud, so that is encrypted and stored there. That's what I told you. Protect stored data using some better standard encryption algorithm like AES, ensures data confidentiality. Okay. End-to-end encryption in the sense, when I store it, of course, it is going from the client to the server, to the cloud. So in between that, some breaches should not occur. Right? You can use the secure system like SSL/TLS. Right? So that's what I say. Encrypt data on the client side before uploading it to the end. Right? Use the SSL or SSL and load it. Right? Only the user with the decryption key can access the data. Make sense? Now, encryption ensures that data remains confidential and protected from unnatural access. No doubt on it. Right? We made it out. Used very interesting encryption algorithms. Everything's fine. Right? But the question is what I highlighted. What happens if a cloud provider is compromised itself, or a cloud provider is not trusted? It sees your data. Then what happens? So the alternate is that let the data owner store the encrypted data. I will encrypt the data. I will create my key. Of course, the present system is not allowing that. Leave out it. I encrypted the data and stored in the cloud system. Then how to? So that makes the challenging now. So okay. So if that is the case, if I keep the encrypted data in the cloud, now the problem comes that if I want to process the data, if I want to do computation over the data, then how will I do? Because when you encrypt it out, it's just what you can say. It is just it is not in proper meaning, right? Okay, the data which is encrypted, everything is the meaning. The semantic has got lost, right? The semantic got lost. Okay, so now how will I compute over that? That makes it challenging. Okay, let's see that. Okay, so therefore we'll see that of course homomorphic encryption was existing. Now let's see that can I use the homomorphic encryption to do it out. So before that, let us discuss about the things that how homomorphic encryption works. Okay, right? Hope everybody understand the encryption mechanisms, right? Right? Okay. So for while encrypting, I will use a key, right? And take the plain text, I will generate the ciphertext, right? And as I told you that the ciphertext is not having any semantic corresponding to your plain text. A good cipher is having that characteristics, right? This is because of the confusion and diffusion of Somanath here, right? So what we'll do is that let derive such a operation, the homomorphic operation, that I will do that operation over the encrypted data, but while I decrypt it out, what operations has been done, let that be preserved. Let me make it elaborate. Let's say that I've given the encrypted of the data A to the cloud or any other party. Then I'll ask that can you do this function F operation with this? Okay. Operation is that what? It could be the addition or multiplication. Because the subtraction is nothing but the negative addition. And division is, I say that inverse addition, inverse multiplications. So these are the two operations I could say, right? Isn't so, right? So I'll say that, okay, I have the data A, encrypted A, I have the encrypted B. Can you do A plus B for me? Encrypted A plus B for me. So that when I download it out, encrypted A, B, I know the key, so that I decrypt it out and I'll get A plus B. Makes sense, right? What I said like this, function F. So I will do this operation over this data which is available here, right? And when I download it, I get this, right? F of E over A, encrypted data, right? But when I decrypt it out, I'll decrypt over this, right? So that I'll get F of A. So what I mean to say that E of F of A is equal to F of E of A. That is homomorphic. Make sense now? Right? Well, so this is the case. Operation over the plain text is equal to decrypt operation over encrypt over the plain text. I take the plain text, encrypted it, and then apply the operations. Once I decrypt it, I'll get this operation over the plain text. Okay, that is it. What homomorphic encryption? Okay. Of course, there are fully homomorphic encryptions are there where you can do both the operations, both addition as well as multiplications. We will not go detail to that part, which will be complicated. I'll come over here. What we used, of course, right? I will tell that the partial homomorphic encryption. So I will take you to one encryption mechanisms, which itself is a homomorphic multiplication encryption, and another is I will tell you that the homomorphic addition encryption mechanism. Okay, right. So what homomorphic means is that, okay, see here in the analogous to this story, all right? The Alice wants to assemble some jewelries. She has some jewelries. You can say that the biscuit golds, right? It is having, right? She wants to prepare something, some ornaments out of this biscuit gold. It is not that biscuit what you had, right? It's something different, biscuit gold, right? Okay. Well, so what you will do is that you will prepare some ornaments. So you go to a goldsmith and ask you to, oh, can you prepare some ornaments like this for me? But it does not trust to this goldsmith. If he gives it, or I think whether you know it or not, nowadays, of course, we are going to the reputed marketplace. And the long list, I'm coming from a very rural village. I know that how the goldsmiths are eating the others, right? They will take these things on a fruit and then do something, and your gold will go out, right? Okay. So, of course, we are victimized, you know it, right? So, maybe the story is like this way. So, what he'll do is that he'll put it in this glass box, metallic box, he'll put. So, he'll ask you that, okay, you take your machine and with this gloves. Okay, what do you do? So if something is there and if you inside, you cannot take it. Right? Okay? So that's what it is, like this way. Test it out and open the box and she does all the things. And of course, finally, she will get these things, right? Okay? So now what exactly the homomorphic encryption does, right? So the second part, what is so-called the cloud, he cannot understand your data. He'll just do the computation what the goldsmith does and give the operated data from this biscuit gold to your jewels. That is it. Make sense now? Well, okay. So see here, just as I told you that there are two types of homomorphic encryptions. One is the additive, another is the multiplicative. Of course, you have the fully homomorphic encryption also, like learning from errors, etc. We will not go through that. Okay. So here, in the additive case, you see that I took the encrypted of M1, the data, operated with encrypted of M2, I'll get the encryption of M1 plus M2. Now see the left side and the right side operator are different. Here I am additive so that put plus. Here this operator could be different. But I need this. So while I decrypt it out, I'll get this M1 for something. Okay. Similarly, in a multiplicative case also I'll do some operation over E of M1 to E of M2. I'll get E of M1 multiplied with M2. So that if I decrypt, I'll get M1 into M2. Make sense now? Okay, I'll take an example so to make it more clear, right? So see here, all of you know the RS executive system, right? So RS executive system says that okay, you choose two large prime numbers P and Q, multiply these two numbers, so that N is equal to P into Q. Okay, and choose an encrypted key randomly, okay, which is co-prime with P minus 1 into Q minus 1. That is what you call the higher prime. All right, and what is this? This is your public key. Okay, E, and the corresponding private key is your D, which having the relation that E multiplied D is equal to 1 mod phi N. Make sense? Okay, all right. So see here, if E of M1 I will do means I want to encrypt the data M1, then it's nothing but the M1 to the power E mod N. Isn't it so? Similarly, if I encrypt the data M2, this will be M2 to the power E mod N. Okay. Now let's stop it together. E of M1 multiplied with E of M2, right, is equal to M1 to the power E multiplied with M2 to the power E mod N. That is nothing but M1 into M2 to the power E mod N. Right? So I say that E of M1 into M2. Right? So now I got this M1 into M2 so that if I lift it, I will get M1 into M2. So what I did here, I took the C1, the ciphertext, multiplied with the ciphertext 2, and after decryption, I will get M1 into M2. So it's homomorphic, right? So the cloud might be having this E of M1, cloud is having E of M2, generated E of M1 into M2. And the corresponding key, what I have not shown here, this is E, right? E of M1 into M2 in this sense, M1 into M2 to the power E. The corresponding D is known to this data owner only, so he can only decrypt these things. So he can find M1 into M2. So even though cloud generated this, he cannot understand what is M1 or M2 or M1 into M2. Okay, now the purpose is solved, right? Similar. So we say that the RSA is multiplicative homomorphic. Similar, but it's not additive homomorphic. You cannot do addition of this. Okay. Let me take a small example here. So if I have this, I want to calculate the area of a rectangle which is there in my cloud. Okay, I will store the data or I will give the data, the width and height in encrypted way. It needs to do this, solve these things and give me this area, which is encrypted area. And I'll decrypt it and get the answer. Okay. So this toy answer says like this way. So I selected the P is equal to 11, Q is equal to 13. So P into Q is 143. That I call it N, right? And public key E is equal to, let's say it is 23 and 143 is my N. And private key is a D, which is key E inverse mod phi N, which is your 47. Of course, P and Q I need to store it out if I want to fast operations. Okay. Well, now what I will do is here is that find this. I said that the ciphertext of width, the CW is width to the power E mod N is 7 to the power 23 mod 140, which ranges to be 2. Similarly, I take the ciphertext of height, what I call CS, which is my height to the power E. E is again my 23, right? So 3 to the power 23 mod 143 N, right? Well, this is 126. So rather than sending 7 and 3, I send this 2 and 126 to the area solver. So you can understand that, whether it is 7 or something else, right? It is just a scrambled text. Okay. So I've given it, and this area solver will do like this way: exactly 2 into 126 is equal to 252, and it's sent pass it to me. For decretion, I will do the same exercise. The corresponding D is your 47. I will do these things 2 to the power D, that is 47 more 143, which comes to the 21, which is nothing but my 7 into 3. That makes sense. Makes sense, huh? All right. So let's see that if I want the addition, homomorphic additions, then I need to use another things. The reason behind this, what I say that the fully homomorphic encryption is a computational intensive. Therefore, my students work in this direction, of course, right? Right. So choose two large prime numbers P and Q randomly, such that GCD of PQ and P minus 1 into Q minus 1 is equal to 1. That means the PQ and P minus 1 into Q minus 1 are co-prime to each other. That's right. And compute N is equal to PQ, and lambda is equal to LCM of P minus 1 and Q minus 1. Okay. Then select randomly G when G belongs to G n square, not Zn, but Zn square, right? Such that GCD of the function L of G to the power lambda mod n square and n is equal to 1. So let me tell that what the L function is that. L function is nothing but L of x is equal to x minus 1 by n. Okay. Well, now compute mu is equal to L of G to the power lambda mod n square's inverse. Okay. And my public key will be n and G. N is equal to PQ and G, what you have chosen from this, right? And secret key is your lambda and mu. What you have already calculated, this is mu, and your lambda, this is lambda is LCM of P minus 1. Make sense? Right. So then what I do, let n be a message to be encrypted. I need to generate a random number in Zn star and compute hypertext C is equal to G to the power m into R to the power n modulo n square. Okay, little bit complex, not to be worried. I'll keep these slides and you work out with a small example. What I kept it here, it will be more interesting to you. Don't worry, right? Then see the mystery of this thing: G to the power m into R to the power n. R is random, right? Okay, right? And compute a plain text m. So what I'll do is that L of L we know that x by n minus 1, all right? X minus 1 by n, right? So this is your L function. C to the power lambda mod n square multiply with mu mod n. This is your m. Okay. Now see the beauty of these things. So what is your CA? That is hypertext of A. If I calculate, this is nothing but G to the power MA R to the power NA. Right? Choose one random number RA to the power N. Right? And similarly CB, G to the power MB, and choose another random number RB to the power N mod N square. Okay. Now if I multiply these two, CA into CB, see the difference now. What I am doing now, additive homomorphic, but I am doing multiplication. So therefore I told that the left side may be different operations. Doesn't matter. I want the right side answer. Okay. So CA into CB is equal to G to the power MA into G to the power MB. That is nothing but G to the power MA plus MB. Okay. Multiply with RA to the into RB to the power n. RA to the power n, RB to the power n. You multiply RA into RB to the power n. Yes, sir. So when you decrypt it now, it is very clear, right? It was, if I say that the M is equal to MA plus MB, R is equal to RA into RB. Here. Right, so if I did it, I will get it, MA percent, right? So that's what I'm doing. So look at this example. If I took it that, let's say, I want to calculate perimeter, present area. Alright? So I took that side A is equal to 7, side B is 3, and side C is equal to 8. And my toy example is that P is equal to 7, Q is equal to 7. So P into Q will be equal to 77, which is, I call it N. N square is equal to 5929.
P and Q would be any number between 1 to 10, or it could be a 22 also.
No, P and Q are the prime numbers. I took it 7 and 11 respectively. Okay, alright. So these are the things. Select G. I took that G as a value in between Zn square, in between 5929. I have chosen this is the 5652. Okay, and the lambda is equal to LCM of P minus 1 into Q minus 1. P minus 1 and Q minus 1. That is nothing but LCM of 6 and 10. 7 minus 1, 11 minus 1. Which leads to me 30, right? And K is equal to L of 6 for lambda mod n square, which leads to the 5652 to the power 30 mod 5929. L, already I told you, that's minus 1 by n, which leads to 51. And mu is equal to L of 6 for lambda mod n square inverse 1 by that. That is equal to 74. So my public key is 775652 and private key is 30 and 74. Right? So what I'll do is that I will encrypt it. I take that is side A, so I call it CA. C means D for M R to the power N mod n square. Let I choose that R is equal to 23. So CA is equal to 5652 to the power 7. 23 to the power 77, R to the power n. Okay. Mod n square 5929, what I told you. And similarly, I did for the CB and CC. The value is like this way. Don't trust this value. I hope it is correct because I too also copied these things from internet. Right? I didn't calculate. Right? Okay. Well. So what I do is that I took this value, the encrypted values, to this server, perimeter server, and perimeter server, what will do? What it will do? Yeah, you see that it's not doing the addition but do the multiplication. That's what I'm saying, right? So it took the things, multiplied this, okay, and then it gives it. Okay. So what I do is that I took the things and I need to decrypt it out. So this is the decryption formula. I took it and I'll get these things. Okay, which is same, right? 7 plus 3 plus 8. Make sense now? Okay. So now we have a little bit of understanding on how the homomorphic encryption works. Right? It will multiplicative homomorphic encryption and additive homomorphic encryption also, right? So note that these are called the partial homomorphic encryption because the RSA works for the multiplication and Wheeler crypto system will work for the additive homomorphic encryption. Okay, this is therefore it is called the partial homomorphic encryption, right? Well, that's fine. So now see that the what will do that multi-party computations, right? This is of course it is not the SMPC actually, but you can do the multi-party computation using the homomorphic tree. Okay, what he told today morning that these are the things called the privacy enhancing techniques. Homomorphic encryption, or you can say that the multi-party computations, these are privacy enhancing techniques, right? Okay, well, so I took this example that there are several hospitals there in Patna, okay, and all keeping the data, encrypted data in the cloud service provider, right? Okay, and of course they are keeping the encrypted data so that nobody understands into the cloud server can understand the actual data of the this is privacy, right? Again, right? So they kept it like this way, and it could happen that some government or some NGO asks such data that the total number of patients in the hospital of Bihar are suffering from cancer. Okay, so how they reply, right? So to answer these things, of course, you will do the computations over this encrypted data, right? Okay. Now, could you mark the difference what I did in the last and this? Can you answer this it out? What the technique we understand? Yet, obviously, is no, because the key for the Paras, key for the Mahavir, and key for the other organization is different. Okay, these key are different, but what we did for area solver or perimeter solver, the key is same. So once these keys are not same, you cannot do it. Okay? That is what happened, right? So I need to do these things of obviously the encrypted data, but clouds needs to encrypt it. What you understand that homomorphic encryption you can do, but the key need to be same. Otherwise, you cannot do it. The data will, the result will be different. That makes a challenge for us, right? So that is what I did. We have considered all parties have the common key, but if the multiple parties with the different individual keys, as in the last example, then how will it solve? Okay, so I'll tell you a story, tell you mechanisms what one of my students has done. This is the things. So the problem is leading to this, that this is the data owner, I could say the Paras, Mahavir, and so on and so forth. They encrypted the data and given it to the cloud service provider, and he has to compute over these things. So the requirement is that I need to have the same key. Okay. So what we did is that to do these things, we use the proxy encryption. So we use a proxy. So I'll convert that all the data over different keys to a data or encrypted data with a particular key. Make sense now? So let's say the Paras is using the key K1 and Mahavir is using K2 and something is using K3. And my proxy, what we do is that it will convert these things, the encrypted data, and re-encrypt it out with the key of proxy. Let's say KP. So this data is also in the KP encrypted, this data also and that data also. So all will get encrypted to KP. So now whatever the computation will be done by the cloud service provider, obviously it's easier task. Make sense now? Okay, so that's what we're doing here. So okay. This Alice will do these things and they re-encrypt the key from the delegator, and this will be given to the one. This is, in summary, this is what we did here. Okay, so crypto systems which allow third party, the proxy, to alter ciphertext which has been encrypted for one party so that it may be decrypted by another. Okay, make sense? So now what we did is that, see here, so this is a little bit mathematics, so not to be panicked, right? I have keeping the slides, of course, if you can confusion, I can write it out. And more detail you can find in the paper. So we created the XA1, B, XB1, XC1 for each party, XA, XB, XC, from Alice and Bob, both. Right? And the XD1 is equal to XA1 minus XC1 divided by XB1. That's the relation. I took it out. I have chosen the XA1, XB1, XC1. And XD1 is equal to XA1 minus XC1 by XB1. These are of course random. XA1, XB1, XC1 in ZP. Okay. Now my secret key is XA1, XB1, XC1, XD1. Okay. Of course, if I don't keep XD1 also, it doesn't make any sense because I can compute it also. Right? And private key is the YA1, which is equal to G to the power XA1, and YB1 is equal to G to the power XB1. For Bob's side, it is just the replica of that. I can say that the Prof is this. My subscript is different. XA2, XB2, XC2, and so on and so forth. Right. So the proxy, what you do is that you generate a key. I call that the RKA1 to 2. Means from 1 to 2. Therefore, we kept that notation. Okay. Is equal to XC1 by XC2, and RKB1 to 2 is my XD1 by XD2. Okay. The question comes that how the proxy will know, that I will tell you in the next slide. It is nothing but they will communicate with each other and he will compute and store it out. This I call the XC1 by XC2, XD1 by XD2. Note that by knowing XC1 by XC2, he cannot understand what is XC1 or what is XC2. Or similar case for the XD1 by XD2, if he knows, he cannot understand what is XD1 or what is XD2. Okay. Right. Now for encrypting, he calculated that C1 of M alpha. The first part is my Z to the power RA, and CB1 of M alpha is equal to YB1 to the power RA, and CC1 of M alpha is equal to YA1 to the power R into M alpha. So actually information is escaping. Other things are requirement for me to compute it out the message. Okay, right? So I sent it out to the proxy, and proxy will do it like this way. See here, RK A1 to 2, so that he can do it now. Now he can do it because it is tuned to that. Now, how it will be, I will tell you next, right? Just you are to the power of XC1 by XC2. So if something is to the power XC2 and you make it power XC1 by XC2, so XC2 cancelled out, we will get XC1. So it is converted to XC1. That is the moral of the story. Make sense now? Right. So that's what I did out. And CB2 of M alpha is nothing but this to the power RKB1 to 2. Same thing, XD1 by XD2. So in the power, you will have only XD1, XD2 and XD2 is cancelled out. Okay, this I no need to touch because it is nothing else. It is only containing your M alpha. So I'll give it out so that he can decrypt it easily. That's what it said. Okay, so now for decrypting, of course, M alpha is equal to this. The C of 2, what is this one? What is A is beta, and divided by this. This is nothing but what I told you. To the power. Okay. Make sense now? So this will be cancelled out and I will get this M alpha. Okay. I'll make it the correctness proof so that we'll make it more clear. So first part what I did is that is how he will generate that XC1 by XC2 and XD1 by XD2. Let me take an example. The proxy generate a random number for creating a blindness and send this random number to the either to Alice or Bob. In either side he can send. So that party will R by XC2. He will not send to the proxy because if he send to proxy, the things are gone, right? He knows this R, so he can find out XC2. So I sent it to Alice. Alice does not know R, so he cannot understand what is XC2. This is her. This is the Bob's secret. Okay. So what does it do is that it multiply with this XC1. So now it is having R by XC2 into XC1 to the proxy. Okay, right. So then, of course, he knows this R, so he cannot know also the R inverse. So he can do this XC1 by XC2. Right? But there is a small key glitch here. You see that key, if it's ZP star. So one is also in the ZP star, right? So somebody asked me a question that what happens with this proxy if sent the value 1? Obviously, if you send this 1 by XC2, we can find out what the XC2 is. Okay, isn't it so? But in that case, also he doesn't know that whether it is 1 or 2 or something else. It is not coming this way. Okay, right? Okay, well, so this means for the even for the D also you can do it out like this way. So correctness, what I told you that how to find this M alpha, this is as follows. That I took the CC2 M alpha divided by CA2 M alpha to the power XC2 and CB2 of M alpha to the power XD2, what I told you, right? right? This is it. Okay, so you can see here that this is nothing but my CC1 M alpha, CC1 M alpha and CC2 M alpha is same, right? I didn't change it up. You remember correctly, right? This is by CA2 M alpha, RKA12 XC2. So you can see here the XC1 by XC2 into XC2, so that I will get the XC1. And similar place for the XD1 I got. And this will be cancelled out, YA1 RA to the power RA M alpha, which is G to the power RA XC2, and YB1 to the power RA XD1. G to the power RA this is nothing but my G to the power RA XC1 minus XB1 D1. What I have, these are having this relationship. So I took that things, right? If you remember that XD XB1 is equal to XA1 minus XC1 divided by XB1. Or you can say that XD1 into XB1 plus XC1 is equal to XA1. Right? So therefore, I could get it out. Right? This, so this for RA to X1 RA and D to power RA X1, and it will cancel out and I'll get the answer. Makes sense now? Right. So I think I will stop it here. And the next of the main, this is the same case because of the plus for the additive homomorphic and the star for the multiplicative homomorphic. I will not bother you much more here. So the objective is that I can make the computation, privacy preserving computation over the cloud without revealing key, right? That was the objective. If you have any questions, of course, I can ask, right? Otherwise, stop it and we'll discuss tomorrow, right? This I think skip it out here. Yeah.